Good day, viewers. I am creating these videos to support teachers of mathematics in helping learners make sense of mathematical concepts and the underlying procedures and processes that go with them. And today what I want to look at with you is addition of fractions. Now, how I choose to look at addition of fractions is ultimately going to come down to how I choose to view the fractions as numbers. And broadly speaking, there are two ways I can view numbers. I can view them as continuous, so as lengths or areas or even volumes, or I can view them as discrete objects. And depending on how you choose to view them will depend on how the addition of fractions looks like. So let's start with a fairly simple fraction addition. Let's start with something like 3/7 plus 2/7. Well, if I'm going to look at these fractions as lengths, then how do I represent a fraction like 3/7 or 2/7 depends very much on the size of the whole. And you can see over here, I've got some Cuisenaire rods out ready to be used. And so normally what I might do is consider the white rod to have a length of 1 whole. And therefore the red will be 2, and the green will be 3, and the pink will be 4, and so on. However, if I want to represent a fraction of sevenths, and if I want to represent any fraction in the family of sevenths, then what it would make sense to do potentially is to use the black rod as 1 whole. And the reason I might use the black rod as 1 whole is because then each of these rods takes on the value of sevenths. So this is 1/7, this is 2/7, the red rod, and the light green rod here is 3/7. And so now if I want to consider adding these things, well, adding lengths like this just means connecting them. So I can take my fraction that is 3/7 and I can connect to that a fraction that is 2/7. And therefore, what is the total length of the number I've created? Well, the total length of the number I've created is equivalent to, and we can see it here if we put the yellow rod next to it, is equivalent to 5/7. It is 5/7 of 1 unit long, 1 whole long. And so we can see here that 3/7 add 2/7 is 5/7, and definitely not 5/14, as some pupils may be tempted to write. We can see that the size of my whole hasn't changed. The size of my whole is still 7. So this is all well and good, obviously, for fractions where the denominator makes it easy to represent. But what about if I want to do something like, I don't know, 3/4 add 1/6? Well, normally, if I wanted to represent quarters, I might choose the pink rod to be 1 whole, because then all of the other rods would take on values of quarters. The white rod would be 1/4, the red rod would be 2/4, and so on. The problem is I can't really represent 6 using that. And similarly, if I was trying to represent 6, I might use the green rod to represent 1 whole, because then all the other rods take on a value of 6. So the white rod 1/6, the pink rod 4/6, the yellow rod 5/6, even the blue rod 9/6. But I can't really represent quarters for that. I've got no rod that is 1/4 of the length of that. So what I really need then is a whole that I can use to represent both quarters and 6. And for that, I'm going to need a length that is easily divisible into 4 pieces and also easily divisible into 6 pieces. And of course, we all know, but learners can soon realize, that probably the most appropriate length there is going to be a length that, if the white was 1, would be 12. So this is 12 white rods long, but I can use that to represent a value of 1 whole. And now I can represent both 3/4 and 1/6 using this length of one whole, because now I can say, right, well, if I look at the green rod is a quarter, and I can see that it takes 4 of them to make the whole. But similarly, if I look at the red rod, that is 1/6, because it takes 6 of them to make one whole. It is 1/6 of the length of one whole. And so if I want to add 3/4 and 1/6, then either I can put up 3 green rods, because that is 3 single quarters, or I could take a blue rod that has a length of 3/4, and I could add a length of 1/6, which just means connecting it to the end of the previous length. And now I can see that I've got a resulting fraction. And the resulting fraction is 11/12 of the whole. But if I then model what I've done there, well, I'm saying, right, well, although this is 3/4, in effect, what I'm doing is I'm treating it as 9/12. And similarly, instead of having 1/6, I'm treating it as 2/12. So I can simultaneously see this blue rod both as 3/4, because it is 3/4 of the length of my hole, or I can see it as 9/12, because my hole is 9 times longer than a white rod, and so a single white rod is 1/12. And similarly, my red rod can simultaneously be seen as 1/6, or it can be seen as 2/12, because it's the same length as 2 of my single 12 white rods. And so this is where numerically I'm able to arrive at the fraction 11/12. And subtraction can be done in much the similar way. Instead of having 3/4 plus 1/6, I could change it to 3/4 minus 1/6, where that would literally be something like that. I have 3/4, and then I come back 1/6, or even something like this, where I have the difference between 3/4 and 1/6, and what would fill this space. And clearly, in both cases, what would fill the remaining space is a black rod, which is 7/12 of my one whole. And so I can model addition and subtraction of fractions in this way using lengths. And the possible benefit of doing this is that we can see the equivalence in there. Now, if pupils are already quite au fait with the equivalence of fractions, I can do the same thing using counters. So I could have here a counter with a value of 1/7, and I could start with 3/7 and then have another 2/7. And in this case, the addition looks like just collecting these things together because they have the same value. And that's important with addition of discrete objects, where we're modeling numbers as objects. We're only collecting them together and adding them together where they have the same unit value. So the fact that these things are all 7ths is what allows me to add them together. But if I now take a counter that is worth 1/4, so that I have 3/4, and then I take a different counter that is 1/6, we can see that I can't really make sense of this sum in any way other than to say it's 3/4 and 1/6. However, if I'm already au fait with the idea of equivalence here, then I might be able to realize that this 1/4 is equivalent to 3/12. And so each of these quarters is equivalent to 3/12. And then similarly, that this 1/6 will be equivalent to 2/12. and that now they all have the same value, these counters. Now they all have the same unit value. I can now add these together. I can collect these together, and I can see the 11/12ths. I can see the 9/12ths. I can see the 2/12ths. I can see the 11/12ths. But obviously, this requires some underlying knowledge of addition, as requiring all of the objects to have the same unit value, and of equivalence of fractions, that I can convert a quarter and a sixth into other equivalent fractions that have the same unit value. Whereas working with Cuisenaire perhaps doesn't have that same limitation, because I can see the equivalence in something like 3/4 and 9/12ths through the representation. So this is my little video exploring addition and a little bit of subtraction of fractions. As always, I'd like to thank mathspot.com and its creator, Jonathan Hall, for the wonderful website that hosts all these virtual manipulatives. If you've never been to mathspot.com, please do go along and have a look. There is a huge amount there for teachers of maths, not just the virtual manipulatives that I'm using for these videos, but all sorts of question generators and other loveliness on there. And if you are interested in using manipulatives and visuals to support learners in sense making, then I would encourage you to go along to my website, visiblemaths.co.uk, where amongst other things you'll find there, you will find a link to my book, Visible Maths, which contains a huge amount of support for teachers in using manipulatives and visuals to make sense of mathematical concepts. And there's a link on there to the publisher where you can see some sample pages and place an order. If there are any concepts or ideas or procedures that you think you would want to see modeled using manipulatives or visuals, then please do get in touch and drop me a line. I'll be making these videos all the way through lockdown and perhaps even beyond. So if there's an idea you want to see, drop me a line, suggest it to me, and hopefully I'll get round to making it for you. Thank you very much.